our next question is going to focus on how do we share the same channel. We already spent a little bit of time discussing the issue when we talk about modulation schemes. Part of the reason that we use modulation schemes is because we do have to share the same channel. But somehow we also have to think about how do we share spectrum. So I would like to really make a parallel story here. When you have a large group of people trying to communicate in a room, and you have to make sure that everybody can be heard, you must come up with some type of a sharing protocol. So either people can speak in different pitches. So somebody speaks at a high pitch, somebody at a lower pitch. That's what we'll be calling the frequency division. So we pick different frequencies for different users. Or we speak at different times. So user 1 first, user 2 second, user 3 third. Or something that's slightly less intuitive, the different language. It turns out that we humans can't do that very well, but even we actually can separate languages even if we don't even know them. So that essentially means different codes, different times, and different frequencies can be used. But more importantly, I want to mention that you can use combinations of those, and in fact, the most advanced systems actually use combination of these techniques. So it would take very long. In fact, we could dedicate an entire semester talking about each one of those. So here I'm only going to scratch the surface and give you some of the fundamental ideas. So let me start with the first idea, which I'm coding here as FDMA, or Frequency Division Multiple Access, which is a very simple idea. It's actually the oldest idea in the world, in the RF world. What you do is you take your available spectrum. So you decide how much spectrum you're going to use. You cut it into small chunks, and each one of these chunks basically becomes the channel, and you dedicate each one of these channels to a user. So this is probably the simplest possible thing that we can do. So FDMA is quite simple. It's also quite intuitive. It works all the time. And in fact, the oldest system in the United States, the analog telephony system, the AMPS system, was basically using this idea. So some of the drawbacks, if you actually think a little bit about how this might work, probably the first drawback that will come into mind is that your number of users are fixed. So that means that, for example, you design this thing to serve 800 users in a particular cell, and next year, now your company is more successful. It has now 1,000 subscribers. Those 200 subscribers can't get any channels. So we're stuck. So scaling up that system actually becomes much, much harder. So FDMA does suffer from these issues, and that's why today we don't use it, at least not exclusively. We actually use it in combination of other schemes, as we will see in a minute. Another idea is, instead of actually dedicating different channels to different users, we can dedicate different time slots to different users, and that's the main idea of time division multiple access. So if you think about that, the way it actually goes is that I'm going to permit each user to transmit basically at simply different time slots. So slot 1 will be for the first user, slot 2 will be for the second one, slot n will be for the last one. And for this time slot, the user can actually use the entire spectrum. So essentially here, user basically takes entire spectrum. So you give all of your resource to all of the users, but just do time division. Now, this technique is actually quite successful, and in fact, it has been used in many, many systems. GSM, for example, is using a combination of time division multiple access with frequency division multiple access. But before I tell you some of those things, let's think of advantages and drawbacks. Again, there are many of them, but one thing that I can say here is that this is a more power efficient technique. Why is that? Is because your PA that we just discussed before, that takes most of your power, is on only a fraction of the time. And so you're transmitting, then you basically stay quiet. When your time slot comes again, you transmit again. So power efficiency actually works in your favor in that case. An obvious drawback is that complexity is a bit higher, mostly because now you have to do synchronization. But honestly, that issue has been addressed well with digital processors that we have. And so complexity is not really an issue anymore. It used to be when those systems were first designed. And as I mentioned, it's possible to do both FDMA and TDMA at the same system. So let me give you an example. So if we basically look at the GSM, I'm going to draw roughly here what happens. In a GSM system, you have 25 megahertz of spectrum that you can use for all of your users. And so what we do there is that we chop this into segments of 200 kilohertz. So these are your channels, if you will. So each channel basically now becomes 200 kilohertz. And within each one of these channels, we actually multiplex 8 users using TDMA. So this is one example of a technique that uses basically everything. You chop your channel, or 25 megahertz to small channels, and each channel is time multiplexed to serve essentially 8 users. The last technique I want to discuss is a little bit different. It's called CDMA, Code Division Multiple Access. And in fact, we'll see 2 different flavors of it. One is basically the direct spectrum, which is this one here. And it's this idea that I can use all my spectrum all the time if only I can assign different codes to different users such that they are totally orthogonal to each other. So if you have n users and you have n codes that are totally orthogonal, then I can actually distinguish those codes. And so here's one technique. We all start from a baseband signal. So this is your baseband signal. These are the bits that you're trying to transmit. For example, this is bit 1, this is bit 0, this is bit 0, this is bit 1, and so on and so forth. And then you basically multiply this waveform with essentially a code. Now, this code is a much, much faster varying signal. You can see here, and this code is essentially pseudo-random. So you decide this code, but it actually looks to an external user who does not know that as a totally random sequence of bits. So if you multiply the green waveform with the red one, you're going to get this purple waveform, which we actually call the chip. And it's actually that chip that gets transmitted through the antenna. Now, if you look carefully here, you will find out that the user started from an actual relatively small bandwidth. But because this has been now multiplied with this code that has a large bandwidth, the final chip has also a large bandwidth. And because of that, because we started from a small bandwidth and we basically spread it around, some of this, sometimes people will refer to this as a spread spectrum technique, because you started with a small spectrum and you basically spread it around. And again, you're using your entire spectrum all the time, except that these codes are now orthogonal to each other. So what the receiver, in other words, will do is that it will take this chip and it will correlate it with essentially the code that it knows, and it will give you back your baseband signal. And since the codes are orthogonal to each other, the receiver will correctly pick the right correlator for each type of user, and it will recover the signal from each user. Now, this technique, even though it sounds a little bit more complicated, has some very, very important advantages. And so one of the advantages is that it's actually pretty immune to interferers and people who are trying to intentionally corrupt you, so intentional interferers. Why is that? Is because somebody who is trying to eavesdrop here does not know your code. And to make things worse, these codes change continuously. For example, somebody could be changing this code 1,000 times per second. So, good luck finding this. And in fact, it becomes practically impossible to crack that. Essentially, an eavesdropper, all that they feel is just random noise. So immunity is basically a big advantage. Another big advantage is that there is a soft limit on users. Why is that? Is because I can always find more orthogonal codes, right? If I generate that with 800 codes and somebody says, can you give me 900 codes? Yes, I can do that. There are the ways that you can basically do that. So in theory, you can actually accommodate as many users as you want without knowing that a priori. Of course, there is a little bit of an issue. In real life, nothing is perfectly orthogonal to each other. And so what happens in real life is that every time you add a user, because of correlator noise issues, your noise level actually goes slightly higher, because the cross correlation between two codes that are not totally orthogonal is not 0. It actually is a little bit of a noise, and every time you have an additional user, you basically increase the noise. So essentially what happens is, after a while, the noise is now high enough, you can't add any more users unless you're willing to, for example, increase the power, so the signal to noise ratio becomes again favorable. So that's why we call it as a soft limit. You can always add users, but you have to pay a penalty. And that is actually much better than a hard limit, because I can always design my system to have trade-offs. I don't like basically hard limits. There are actually many other things I would mention, but for the sake of time I won't. Now let's talk about drawbacks, because nothing is free in real life. And so the first drawback I already mentioned is that every single new user essentially leads to higher noise. So that is clearly a drawback. I can deal with it, but it's not really a very good idea. The second thing is that there is something called near-far effect, which is a direct consequence of that. Here's what I mean by near-far effect. So let's imagine the scenario of many mobile users. There's a base station. Let's say that I'm the base station. The person who is very close to me is actually transmitting a very large signal, while the person who is far away from me is transmitting a very weak signal. That means that the noise that we talked about here, added by the loud user, is actually far worse than the noise added by the far away person. And so what happens in those systems is that if it turns out that if somebody decides to either be very close to the base station or actually transmits very loudly, it will actually corrupt the noise for everyone. That's a very famous near-far effect. And in fact, we do deal with that on an everyday basis. Many 3G systems today are actually using CDMA techniques. And the way they do that is that constantly the base station listens to how loudly you speak and sends you back a note that says, hey, tone down, you're too close to me. Or you can actually transmit a little bit higher, I can't hear you well. But there is this constant feedback all the time that must happen to basically keep the near-far effect under control. Now, because of that, there is another technique, another CDMA technique that uses very similar ideas, but different implementation. And this implementation is called frequency hopping. It's a very, very simple idea. It basically works in exactly the same way as the FDMA, except that the channel allocations are not constant. So in the time slot number 1, user 1 gets the first channel, user 2 gets the second channel, user 3 gets the third channel, and so on. A millisecond later, now the channels have been changed. The first channel goes to user 3, the second channel goes to user 4, and so on and so forth. So you have this constant frequency hopping where the frequency allocation changes as a function of time. Many of the advantages and drawbacks are actually similar to what we discussed before. The main additional advantage of the frequency hopping is the near-far effect is not there. And so that should be obvious since the FDMA does not suffer from that. The obvious drawback is that you need very precise timing. So essentially your local oscillators, switches, and everything actually designed becomes more sensitive here. Now, frequency hopping techniques were actually utilized first in defense systems because we wanted to make secure communications, and that's a great way to make a secure communication. Nowadays, you can find them actually in commercial systems as well. For example, Bluetooth 4 is actually utilizing a frequency hopping technique. I have some numbers here, maybe I can share it with you. In Bluetooth 4, there are actually 40 channels. It's 1 megahertz per channel. And that allocation actually changes 1600 per second. So there are 1600 hops per second in Bluetooth 4. So hopefully that gives you at least a glimpse of some of the techniques that we can use to share channel based on time, based on frequency, or based on code